great both chance to see people that I've had a chance to not get to meet before and actually talk to, and also learn a lot. So I'm going to tell you a pretty short story. I'm going to take the 20 minutes seriously, I hope. First of all, I'll give you a bit of a background into what our lab's been doing the last few years in sort of technology development that I think is somewhat useful for studying kinases and post-translational modifications in general. And then kind of bring it to bear on one very specific problem that's near and dear to many of the people in this room, which concerns protein kinase A and the nature of one of the autophosphorylation events. So many years ago, when Steve Burley and John Currian recruited me to Rockefeller, I was interested in what was then, and except for maybe some of the people in this room now, is still considered a very esoteric problem, which is how the phosphoryl group gets moved from ATP to the hydroxyl side chain of serines and tyrosines. And at the time, and maybe even today somewhat, there was a controversy as to whether the nature of the transition state looked more compacted, so-called associative, or looser, so-called dissociative, and how the enzyme might catalyze either of these two reactions. And I should say that in the many decades of physical organic chemistry literature before we began to try to study this problem in kinases, there was a sort of general consensus that non-enzymatic phosphoryl transfer followed this bottom pathway, a more exploded transition state in which the leaving group ADP largely departed prior to the attack of the hydroxyl group. And this problem motivated us to try to study this using a classical physical organic chemistry approach. And that approach basically involves changing the nucleophilicity of the substrate. So in this case, we used a series of tyrosine analogs that were incorporated into synthetic peptides, but differed only by virtue of having various fluorine atoms in the aromatic ring, so that it allowed the basicity of the hydroxyl to be altered. And so you can see that when you don't have fluorine atoms in the ring, the pK of the side chain hydroxyl is around 10. When you have 4 fluorines, it's 5. And when you have an intermediate level, it's intermediate. And as control peptides, we also put other substituents in the ring that could change maybe interactions with things, but wouldn't change the pKs as much like these methyl groups. And after making many analogs like this, what we learned was that the rate of the reaction, of the enzyme catalyzed reaction, was largely independent of the basicity. And this is characteristic of more dissociative pathways. And so it's probably not really fair to put a big dark X here. It probably should be in dashed lines, because you can never really prove a mechanism, or even very hard to even disprove one. But based on a number of other experiments as well, which I won't get a chance to go into today, we currently favor this pathway, and I know some of the people in this room have done computational work and other experimental approaches that lead them to favor this arm of the pathway as well. So an independent way to potentially test this would be to see if one could design a compound that might be a transition state analog, if you will. And for those of you who are more organic chemically inclined, you'll recognize the challenge of trying to make something that looks like this, with very weak bonds between an ADP moiety and phosphorus, and on the one hand, and a peptide and a phosphorus. There have been prior efforts to make bisubstrate analogs inhibitors against kinases, and one of the early efforts was George Kenyon's group, which directly hooked up an ATP with a peptide, and they used the classical chemtide sequence here. And as you can see, they got a fairly modest inhibitor. And what one could maybe deduce from the proposed transition state is that if you directly hook up the serine and the phosphorus, this might be too close, and you might be creating a lot of strain. And so, simple-mindedly, we thought if we just put a spacer between an atom that was the phosphorylated atom and the ATP moiety, and the guess for the length of the spacer was based on some work of Alan Miliband and others, and also from structural studies, that if you had roughly around 5 angstroms, this would be a good thing. And this original bisubstrate analog, if you will, was designed against the insulin receptor kinase, because at the time we were collaborating with Steve Hubbard. And what we found was that we did improve inhibitor potency. We didn't create the kind of transition state analog that super duper enzyme transition state analog inhibitors have, which can be femtomolar, even if you've heard Bertrand talk. But we made an improvement over simple ATP analogs or simple peptides. So we got some additivity of the two ligands. And this was somewhat satisfying. It also turned out that this nitrogen was hydrogen bonding to the catalytic aspartate base, as we proposed. And in some cases, the carbonyl, which was put in for synthetic ease, is utilized as a magnesium ligand. And I should say, right around that time, we collaborated with Hubbard to get a crystal structure, and the compound roughly bound the way it was proposed to, the peptide moiety bound to the surface of the C-lobe, and the ATP was in the right spot. And over the last several years, our lab and other labs have continued to try to explore the generality of this approach, and also to use these kinds of things as tools, mostly in structural studies. Some of the more successful cases, in addition to the insulin receptor kinase study, have been in collaboration with John Currian on ABL and EGFR, and collaboration with Louise Johnson on the CDK2 problem. And we hope someday with Joe and Gori on, this is actually an SR protein, and some of the other cases as well. You can see that our affinities vary quite a bit. So the one with Louise was exceedingly potent, 1 nanomolar, but that was in large part because of an extra docking sequence in this peptide motif. And in other cases, we are quite a bit weaker. So with EGFR, the potency is on the order of 20 to 30 micromolar. And we don't fully understand that. So does that mean that enzymes are changing? These kinases don't have conserved transition states. We don't really favor that idea. We think that it's probably the happenstance of having metal ions in slightly different positions that maybe screw up some of the interactions. But one of the things that we wanted to try to do lately with this approach is to examine the nature of autophosphorylation events. And many of you in the room know that many protein kinases are regulated by autophosphorylation. In most cases, I think people believe these autophosphorylation reactions are trans, meaning one kinase phosphorylating another kinase molecule. But in some cases, people believe these are cis, or truly intramolecular autophosphorylation reaction. And yet, it's been very hard to really nail these models down. And so the idea would be if we could insert this sort of bisubstrate analog piece into a kinase at a site that's thought to be a cis autophosphorylation event, maybe we could obtain novel evidence for that kind of confirmation. So to do that, we needed to go beyond just making peptides with ATPs. We had to insert these into proteins. And fortunately, our lab also is a developer of this protein semisynthetic method called express protein ligation, which for some of you will have seen before, but for those of you who haven't, involves the ability to link recombinant protein pieces with synthetic peptides. And the power of enteins is used here so that you are able to install these reactive thioester moieties using enteins at the C-terminus of a recombinant protein piece. And then these enteins, these thioesters can be utilized in a very chemoselective reaction involving an N-terminal cysteine in the synthetic peptide. And this rearranges, a la Steve Kent's early findings to a standard peptide bond, and you end up with a semisynthetic protein, which allows you to incorporate synthetic materials into this blue part, which can then be natural things, of course. And so the idea would be, if there was a protein kinase that was phosphorylating in this blue part, then we could stick an ATP there and then examine the conformation of that semisynthetic protein. So we thought a potential test case of interest would be protein kinase A, which has been obviously well studied here. And we know that protein kinase A is regulated by two phosphorylation events, one of which is catalyzed, as we've already heard, by PDK1 on its activation loop. And then a second is a phosphorylation near the C-terminus on serine 338, which is believed to be intramolecular. And of course, as I mentioned, there could be two models for the intramolecularity. One is a sort of a trans model, where one kinase is phosphorylating a second, and the other would be a cis variety, where in this case, the C-terminal piece would come into the active site and get phosphorylated and then presumably released. And Susan Taylor's lab obtained some very important evidence for this upper model, which again is considered to be the less common variety. And that evidence included the fact that she showed that you couldn't take an active kinase and phosphorylate an inactive kinase on its C-terminus. And she also examined the concentration dependence, which was more consistent with the cis event. So this we thought would be a really interesting one to try to apply this technique to. And so what that amounted to in practice was to essentially build a synthetic peptide of the C-terminus that has an ATP attached, and this is the kind of chemistry that we use. We use an ATP gamma S for chemoselectivity, displacement of the bromide here. Note that we have an aminoalanine rather than a serine, and this is, again, allowing us to hydrogen bond to the catalytic base. And then we needed to make most of the recombinant pKa fuse to an intine, and then we carried out this chemical ligation, as I mentioned, and we made what we call pKa-ATP, the pKa that's fused to ATP at this particular serine 338. And as a control, we also made an inorganic or phosphate equivalent of this, so something lacking the ADP moiety, which we believe would not be able to perhaps undergo the conformational change associated with an internal motion here. So these materials were made, and we got reasonable quantities of them, reasonably pure. Fortunately, the way we chose to make this still allowed the activation loop. We didn't need to use PDK1. Taylor's lab and others had shown that when these proteins are made in E. coli, they are, even though PDK1 is probably the in vivo kinase, they can autophosphorylate on their activation loop, and that seems to be the case for this is just standard recombinant full-length pKa, the ATP fused one, the phosphate fused one, and then a commercial pKa that we also tested. And importantly, we wanted to find out if these things were oligomeric, because one could imagine that if you had an ATP in the tail, it could attract another kinase to bind to it, and then you could have a string of these things. But by size exclusion chromatography, pKa-ATP appeared to be monomeric, as did the expected phosphorylated version. So in order to interrogate whether there was a conformational change, the first thing we did was borrow a method that Joe Adams' group had developed some years ago to explore affinity for ATP analogs. In this case, we used MANT-ADP. And Joe's lab, I think, had shown for the first time that if you take MANT-ADP and if you excite the tryptophan fluorescence of pKa, you can essentially transfer that fluorescence energy and excite the ADP. So if you excite at 290, I should say, you can get an enhanced MANT-ADP fluorescence when it was bound. And so using this, we were able to measure the affinities for MANT-ADP for the two semisynthetic proteins that we made, pKa, ATP, and pKp, and you can see that there's a tighter affinity, I should say a tighter affinity for MANT-ADP with pKp, and a weaker affinity for the one that has the ATP in it, but this is about a four-fold difference in affinity. So not a massive difference, but a measurable one. And likewise, there was a four-fold difference in kinase activity. We didn't do a full spectrum of kinetic parameters, but we showed that fusing the ATP at the 338 position reduced the activity by about four-fold. So both of these things are consistent with the idea that the ATP of the C-terminus could be entering at least partially or in equilibrium and making the active site less accessible to an ATP molecule, an external ATP molecule. We also tried some partial proteolysis using trypsin and compared the sensitivity of trypsinolysis of these two proteins. And you can see that, although this is kind of a dirty gel, we got some protection against proteolysis, and particularly with the generation of sort of this intermediate fragments with the pK-ATP as opposed to the pKp version. Again, consistent with the idea that there's either a conformational change and or an occupancy of the active site. It turns out that this one fragment that did sort of stabilize here was clipped at somewhere around amino acid 80, which is in the region of where the C-terminal piece crosses over in three-dimensional space with the rest of the kinase domain. And so our working hypothesis from this data is that there's an equilibrium in the ATP-linked semisynthetic protein that favors this more closed form versus the more open form here. It's not a million to one. It's probably, at least based on our limited data, on the order of 4 or 5 to 1, favoring this closed form versus the open form. So this ATP is, we think, able to maybe drive it into this state to some degree. Now, although we'd love to get a crystal structure of this, in the absence of that, we developed in collaboration with Jeff Bray's group at Hopkins, who's an expert in the use of Rosetta, and he worked with us to try to model a conformation that would correspond to a cis autophosphorylation. So shown on the left here is a crystal structure determined by folks here of pKi, ATP, and the kinase domain. And labeled in green here is the C-terminal tail, showing its classical pattern. What was done in the modeling exercise was to conserve the first 20 or so residues of the C-terminus, which is highly, across the many, many structures that have been done, is highly conserved in these structures. And also the what's called the phenylalanine clamp at the end, the last few residues of the C-terminus, and then to let fly roughly residues 314 to 346, I believe, which include the serine that gets phosphorylated and residues that are most loosely conserved structurally in the various structures. And then what was done was to place the serine 338 as a constraint so that it would be roughly in the position of the alanine of pKi, the site that gets phosphorylated. And using that, those constraints, one was able to develop a relatively low energy conformation. Actually, it was done in two pieces, N-terminal to the serine and C-terminal to the serine, but one was able to develop a conformation that was plausible for autophosphorylation. And if you look close up at that model, you can see that even though these weren't put in as constraints, the arginine that's two residues upstream from the serine is making contacts that are somewhat reminiscent of the arginine in pKi with a conserved glutamate residue that's here. And then hydrophobic residues of the C-terminus are able to make hydrophobic contacts here. So these were sort of what Rosetta Gate spit out. So our working model is that this cis autophosphorylation is plausible, and that one can make a suitable model for it to occur. And the question is, can this type of technology be extended to other kinases? And I think that's a direction that we want to take in the future. So happy to take any questions. And these are the folks that I want to thank in doing this work.
Questions for Phil? Were you surprised that the effect of locally tethering the ATP was actually as small as it is?
So yeah, I actually thought that it might drive it in like 1,000 to 1. And an artifactual reason for why it was that small is that 10 or 20%, say 20% of our semisynthetic protein is somehow damaged in a way. And so that part is still very accessible to ATP. It's very hard to rule that out. So it is possible that that's a lower limit for what equilibrium is. If it's not a lower limit, if it's the actual value, then it might speak to the fact that there is some strain, in moving that piece into the active site. And so that's sort of the conundrum we have. Well, so we think that the fluorescence binding was the maybe reflection of the affinity for external ATP. So the fact that man's ADP bound about 4-fold less well suggested to us that was the that was a reflection of that. But it's conceivable, I guess, that if 20, I guess if you're, yeah, so I guess your argument would be if 20% of the enzyme was doing all of the was essentially doing all of the binding, then the KM shouldn't be affected. And I guess the fluorescence data are somewhat argues against that. So, but we didn't actually get a KM for ATP because it turns out that we didn't make enough to actually do really good steady state kinetics and saturate with peptide and all that sort of thing.
Can you do just the size of your linker between your ATP? Could you re-explore that easily?
So it's not easy to make lots of different variations of that for, doing chemistry with nucleotides and peptide conjugates is, is a pretty messy area to be working in. We have done some playing with that, not in this system, but in simple peptide analogs, and we've not been able to improve upon the link we have. We've probably made about a dozen modifications.
So basically related to this whole thing, but your bisubstrate for the series tuning kind is even though the one structure is there with CDK with this conjugate. But I don't think the ATP is there. You don't see the density.
Yeah, so it's actually a good point.
It's a very high affinity, but you don't see that.
We've never gotten. I know where your question's going, but if your question is, does this work less well for serine threonine kinases in terms of structural studies? The answer has been yes so far. We haven't had that many examples of trying, but and with the case with Louise, as I recall, although the ATP was seen, there wasn't a lot of the local amino acids. So don't know why. We don't think they're getting destroyed, but they seem to be flexible.
And in our case, we tried with both SLPK1 and SCI1, the same story. We see this is ATP portion. We don't see the peptide.
Yeah.
Right? So now it works so beautifully with this lucky tyrosine kinase people.
Yeah.
Do you have any idea? That's very important that we get something. Is it why it is?
I can't say that we've done enough experiments to know for sure that it's a general phenomenon yet. I mean, we've tried with you guys and we tried with Louise, and actually we did try with PKA before I got to know Susan while we were working with her colleague in Germany, But in no cases have we seen the amino acids. So it's a good question. I don't know why. But yet they can bind with reasonable affinity, so it's not simply an affinity issue.
Tony?
Oh, Phil, how effective is the ATP-linked peptide as a bisubstrate inhibitor?
So right, so the chemtide, I can go back to that, I think. So chemtide, which is not the C-terminal tail, we haven't done it on the C-terminal tail, has an apparent Ki of 3 micromolar, which is obviously not super duper, but the peptide alone has an affinity of somewhere around millimolar, so it's far tighter than a free peptide, but it's not like a standard potent transition state.
Right, but it might be important to test the tail peptide, right? I mean, does it have additional docking information?
That's actually a great idea. We haven't done that. Yeah, thanks.
That was why I talked about CDK2 site and maybe substrate is so good, because it has a docking site. The RXL downstream gives the combination of those two receptors or the RXL there. But it goes back to the point of cis phosphorylation, because that has like an inherent docking site because it's already localized, because it's part of the kinase that's phosphorylating it. So you would expect it to have a relatively low Km. Tightly bound, because it has, in terms of entropy, it hasn't got far to go. Now, a catalytic reaction that has a low Km has an inherently low Kcat. Because if you think of it, you have enzymes for substrate 1 energy level, enzyme substrate complex over to the transition state. If your enzyme substrate complex is too low, it has much farther to go to get over the transition state.
Right.
So I think that was what we were also discussing earlier with our SPK, SRPK. Again, once you have a docking site, if you have too low a Km, your Kcat is also reduced. Maybe biology has good reason for exploiting that, but I think that physical chemistry, that's the way it's going to go.
Sure.
So, a couple of things. So I'm thinking with some of these things with PDK1 and looking at the docking of the complete ATPs, that if you mutate like the phenylalanine that's coming from the C-terminal tail, I think Jay has a poster on that. And that's very defective in binding externally ATP. So you kind of recruit that. But you were surprised that you see, we've done a number of kinases now overlaying with PDK1 and seeing this ATP binding site being a good docking site. But in the piece in the middle, that little phosphorylation site that you're looking at here is what people call a term motif. And it's very sensitive as to how that gets phosphorylated. I think it's different with the different kinases. Like AKT, there's an external kinase that does that. And so what we find with the hydrophobic motif, that it doesn't get recognized very well by itself, but if you phosphorylate that serine 338, then the hydrophobic motif gets recognized very well in the peptide array. And so it's almost as though you would have docking initially to that ATP binding pocket. That would be a cis autophosphorylate, the kinase, the pKa would phosphorylate that tail one. And then that would facilitate binding to the hydrophobic motif, which would now make it easier for PDK1 to phosphorylate the activation loop of pKa, so that you could have this very complicated crosstalk between different kinases and very highly regulated.
Well, so actually you just made me think of something. Should we try throwing in PDK1 to see if that will influence this equilibrium? In other words, when it binds to PK, even though the activation loop's already been phosphorylated, would it drive the loop more into, would it drive serine 338 into the active site? You haven't tested that, but I don't know what your feelings would be on that.
Yeah, I mean, so one of the students, John, has been looking at a 194 alanine. That doesn't get out of phosphorylation, so it's a great substrate for PDK1, and you can look at the single phosphorylation of that one independent of the activation loop being phosphorylated. So it's possible to do that. The other thing I'm wondering, because you see there's 2 cysteines in pKa, and there are conditions where you can cross-link them. And there's one is it's 199. All of these AGC kinases are very reactive there. And the other one is 343 up at the C2.
I think we mutated the one out that I think to prevent that from complicating our lives. So we mutated the one that's known. I think that you and others have shown organomethyl, but I didn't.
It has to come down into that pocket. We haven't perfectly. It has to come down in that way to be able to make that disulfide bond. And so again, we're just trying to get a structure. All of ours have been phosphorylated. So what happens to that tail when it's in its dephosphorylated state? And I think because it's preceded by all these negative charges is why you would never have a trans autophosphorylation, because you've got 6 negative charges there, and the tail.
So that maybe gets at Tony's point, which
Right.
is we should just measure that peptide with a ATP there and see whether it is weaker as suspected in chempa.
Yeah. Then I have another question about the transition state, because in our transition state analog, you wouldn't have room to put in much extra. You wouldn't have room to put in those 5 extra things. I mean, it's very tight, it's very constrained right at that active site, so you wouldn't have the opportunity.
So it's fair to say that ours is in a transition state. I like to think of it as the ground state that would precede the transition. It's definitely not a transition state because we're not halfway. The phosphoryl group is still attached, if you will, to the entry group in a sense. And so I don't think that we're it may be the kind of very beginning of the reaction coordinate towards the transition state, but I think that it's not like a vanadate or an aluminum. It's not that.
And so when either you or John or with the tyrosine kinases, so with the serine kinases, you have this lysine, so it's the acidic 166 in pKa right at the beginning of the catalytic loop. That's a weak catalytic base. And then 2 residues there. You have a lysine, which is really bridging the gamma phosphate, and then the glycine loop is on the other side. So it's a really good, you're just trapping that gamma phosphate. And then in the tyrosine kinases, you have either an arch, an ala-ala arch, or an arch ala-ala. And that arch, somehow, it doesn't do that in most of the structures. I think we found one where it did, where it came over, that arginine did come over and actually contribute to stabilizing what would be the phosphate of ATP. Do you know anything about that?
Yeah, so our model, that's the one that we complement with. So when we mutate that arginine, we can complement it with imidazole. And our hypothesis is that it's not interacting with the phosphate, that it's interacting with the tyrosine side chain and the catalytic base in a triangle of hydrogen bonds. But of course, these are all crystal structures that are not, we don't have a transition state model. Okay.
What do you mean the tyrosine side chain? It's going like an
It's actually yeah. So the I don't have that structure in this easily handy, but the oxygen lone pair is giving us a lone pair up to the arginine guanidine side chain. Maybe should we call it? It's like
Yeah, well, after break.
yeah. So maybe I'll take questions.